Many people think vector search alone is enough. Then they realized that the old good BM25 full-text search can improve the accuracy. That's the hybrid search. But did you know there is one more technique that you can add to that hybrid search, which can take your RAG retrieval to a completely different level? Hey, it's Michał from deployedinazure.com, and today you will learn how semantic ranking in Azure AI Search uses cross-encoders to fix weak matches, boost relevance, and improve the answers your RAG system returns. And the best part, you will see exactly how it works in practice. We'll break down Bi-Encoders and Cross-Encoders and why they behave differently, L1 and L2 retrieval phases in Azure AI Search, how answers and captions can enhance user experience, and a real C# example which covers all of these topics. Let's dive in. Hey, let me quickly and concisely go through today's example so it's clear to you what we'll be talking about. Let's assume we are working for a fictional travel agency, the Galactic Voyages Company, and we are asked to build a very simple and primitive FAQ system. And that company owns a fleet of starships, and this is our data source. There are 10 starships, just as a simple JSON file. What we'll be doing, we'll be pushing that data to Azure AI Search, including vectorization of the overview property. So we have an index in Azure AI Search, and we'll push that data to that index, and then we'll perform that search operation. And this is how it looks like. So we'll be testing 4 methods, just that ordinary full-text BM25 search, then hybrid, which means BM25 plus vector, then hybrid plus semantic, and then something extra, hybrid plus semantic plus scoring profile. Let me invoke it. Provide a question on fast and prestige. As you can see, there were such results returned, including the answer and top 3 most similar documents plus captions. You can also see that some part of the text is highlighted, and we'll talk about it. If you look at the result number 1, you'll see 3 score-related properties. It's score, it's reranker score, and it's reranker boosted score. By the end of the video, you will know exactly what each of these score attributes means. Let's not waste any time and let's talk about it. Semantic ranking in Azure AI Search behind the scenes uses cross-encoder. And this is something I would like to explain first because I believe it's really necessary. Okay, it maybe isn't strictly necessary to know all these mechanisms which are invoked behind the scenes, but it's very useful in some cases. To explain cross-encoder and how they differ from Bi-Encoder, let me start with that diagram. This diagram features a very simple RAG pipeline, which is based on a pure vector search. So one more time, user writes a prompt, that prompt is converted into a query vector. And then that query vector is compared with all of the remaining vectors which are saved in vector database and which were initially created based on some data source, for example, some company documents, some PDF files. So what we do, we take that query vector, we ask the vector database, hey, given that query vector, give me the top 3 most similar vectors. And once we have it, then we may forget about vectors and vector similarity, because what we care about is the data based on which these three most similar vectors were created. For example, some data chunks, text chunks. Once we have these text chunks, then the remaining step is to just create that final prompt where we embed user question in conjunction with these retrieved text chunks. Then we just send such a prompt to an LLM and it provides answer which is grounded in that specific data coming from the data source. And what I just described is Bi-Encoder, which is opposite to Cross-Encoder. So what Bi-Encoder means is that your query vector and your data source vectors are created completely independently. In other words, the embedding model, which is responsible for producing these vectors, never sees user query and these data sources, for example, text from these data sources, together. It works completely independently because you first vectorize your data sources ahead of time, and then while searching is performed, then you only have to convert that user prompt into a vector. So it's very scalable, very fast. But one more time, embedding model has never seen user prompt and the source data together jointly. So that's the Bi-Encoder. Now let's talk about Cross-Encoder. So the main idea behind Cross-Encoder is that it is just a neural network which can answer such a question. Given that user query and given that document, how similar these data chunks are, how similar they are to each other. So the output of it, you can think of that output as a relevance, where higher relevance means that they are very similar. But the main difference is that Cross-Encoder analyzes that data jointly. So the input to that Cross-Encoder is, for example, that query and the document from the index. It's very accurate because of that. But there is one downside. It's computationally heavy, and therefore it's very slow comparing to the Bi-Encoder, which you can see on the left side. So it's high accuracy, but it's slower. And for Bi-Encoder, accuracy is pretty high, but comparing to Cross-Encoder, I would say it's moderate. It will never be as accurate as in case of Cross-Encoder. So the question arises, so how does it work? And we'll talk about it in a second. And this is something which is related to the L1 and L2 retrieval phases. What I would like you to remember from that chapter is that we have Bi-Encoder. This is that ordinary architecture with embedding model creating vectors for your data source and turning user prompt into a vector, just creating vectors completely independently, whereas Cross-Encoder analyzes that user, for example, query and document content jointly together, and therefore it's more accurate. And now let's talk about L1 and L2 retrieval phases in Azure AI Search and how it's related to that slow Cross-Encoder. See you there. Now let's talk about L1 and L2 retrieval phases in Azure AI Search and in many search engines, really. So the L1 is BM25 in conjunction with vector search or just a pure BM25 or a pure vector search. But the bottom line is the L1 phase is extremely fast. So it scans the full index, it returns pretty accurate results, especially when you combine these two methods, BM25 and vector search. And just a reminder, that function which combines these results when you invoke BM25 plus vector or vector plus vector is called reciprocal rank fusion. It's a simple math formula which looks at one result set, at the second data set, or yet another data set. It looks at the ranks of each of the documents within such a data set and then just combines the results. So it alone improves accuracy greatly when you combine BM25 and vector search. So this is our L1 phase, and thing to remember, it's very, very fast. So high speed is something which we can remember about that phase. But the end of that phase, what we can do, we can select top documents which will be then passed to the L2 phase. And we can pass to the L2 phase up to 50 documents. I'm recording that video in March 2026. So currently the limit is 50. And you may ask a question, why only 50? It's due to that limitation of cross-encoder, which we talked about during the previous chapter. So one more time, cross-encoder is very accurate, but also quite slow. And therefore, there is that limitation. So L2 phase is just invoking our cross-encoder based on the top documents returned from the L1 phase, thanks to which cross-encoder can re-rank the documents which were passed to that L2 phase from the L1 phase. So that's it. I think that that's all we need to know for now in terms of some theoretical background. So one more time, L1 very fast, high speed, L2 way slower but more accurate because it uses cross-encoder behind the scenes. And by the way, you may wonder what data was used to train such a neural network for that cross-encoder. In case of Azure AI Search, that data mainly comes from the Microsoft Bing search engine. So as you can imagine they've had quite a lot of data to build a very specialized neural network which can analyze that similarity very precisely. That's it about theory. Let's talk about some real implementation now. See you there. In order to use semantic ranking in Azure AI Search, we must first enable it because it is considered a premium feature. So this is my Azure AI Search instance, and if I go to premium features, you'll see that I've already enabled it. But if you haven't, then you have to do so. And as you can see on the right side, it's quite expensive, I would say. So you need to be aware of this additional cost. So it's not just the cost of the Azure AI Search instance itself. This particular capability will also cost you some additional money. So one more time, we have to enable it. But sometimes when you use some workflows, like for example, import data new, and then through the portal, you just click to import data from blob storage or from somewhere, then behind the scenes, such a workflow can enable that feature automatically for you behind the scenes. So that's just a note. Now let me show you how it's configured. So here is my index, and it consists of a few fields, and all of these fields is what you could see in that JSON file at the beginning. So we have all these fields, including overview vector, which is a special field. And now if I go to semantic configurations, you will see that I defined default semantic config. If I open it, you will see that such a semantic configuration consists of three sections. It's the title field, which is usually a document title, product name, or some concise identifier. So we have title field. Then we have content fields, and this is what matters the most in terms of that semantic reranking, and you should put here a field which stores just some description in a natural language. And then we have keyword fields. So for example, I selected category and features, but one more time, the most important section is content fields. And you can see that I can add a few field names to the content fields and keyword fields. So how does it work? Behind the scenes, such a config is needed because when that comparison in that cross-encoder is made, then it doesn't take your raw document, meaning everything you store in your index. It creates something which is called a summary string. And as you may guess, this summary string is created based on what you specify here. It's not something unlimited in reference to the length of such a summary string. So the current limit is 2048 tokens, where for the title field, you can use 128 tokens. For the keyword fields, you can also use 128 tokens, whereas for the content fields, you can use all of the remaining tokens. And you may provide a few field names, but if you exceed that threshold, then it will be just truncated. So, for simplicity, let's treat a token like a single word in English. It's not precise, but we can make such an assumption. So one token, one word, roughly, at least in English. So this is our definition. And please remember that concept of a summary string. Now, if I go to the JSON definition here, you will see that what we could see on that UI a second ago is just represented here as a JSON. And you see prioritized content fields. Pay attention to that prioritized content fields, which means that the order of these fields matters. And we have title field, then we have a ranking order, and we have boosted reranker score. That's a default option, and I will explain that a little later. Then we have flighting opt-in, false, and flighting opt-in means that you can use some models which are not publicly available yet. So it's more for experimentation. I don't encourage you to change it to true in your production application. And then there is one thing I would like to focus on, which is default configuration here. As you can see, configurations is an array, which means you can add many semantic configurations. How many? Up to 100 per index. And another important thing is that you can add them or update them at any time. So, it's not something which requires rebuilding the index or anything like that. That default configuration I selected here gives me such capability, then when I'll be invoking my queries in C# code, I don't need to specify which semantic configuration should be chosen. So even if there is one, but you don't specify default configuration, then you must always pass that semantic configuration name, in that case, default semantic config. Yeah, so that's it in that section. So let's carry on. Before we carry on, there is one more important detail to remember about. When you create a semantic configuration, then of course you cannot choose whatever field from your index. Field which is allowed to be chosen in that semantic configuration has to be either string, collection of strings, or any string subfield within a complex type. There is such a type in Azure AI Search, complex type, where you can put some JSON-like object embedded into your index. So one more time, it's string, string array, or just a string subfield of a complex type. And it makes perfect sense, right? Because semantic ranking is all about analyzing that text, especially the fields specified in the content fields section. But there is one more thing you need to remember about. Such a field with such a type also must be marked as retrievable. So if it isn't marked as retrievable or it isn't marked as stored, you can see there is also such a property stored, then you cannot use it within that semantic reranking phase. And it also makes sense. First of all, if you want a field to be retrievable, it has to be stored. So once it's stored, then it might not be retrievable. You must mark it as retrievable. Only stored true in conjunction with retrievable true allows you to choose such a field in a semantic configuration. Just something to remember about. Let's continue now. Now let's analyze a basic semantic query in Azure AI Search. I will use Azure Portal and then we'll analyze our C# example. So the most important thing is that query type here. It can take three values. It can be simple, it can be full, which behind the scenes would use Lucene query syntax, and it can be also semantic. You may wonder, so then can it be both Lucene plus semantic if we are forced to choose just one query type here? Yes, it is possible, and I'll show you later how. And then we have captions and answers. And I just specified extractive for both, meaning that I want these captions and answers to be returned. And speaking of captions and answers, let me briefly summarize the three main features of semantic ranking in Azure AI Search. Of course, it has that capability of analyzing these top 50 up to 50 documents from the L1 phase very accurately. That's the most important advantage and feature. But then there are three more. It can return an answer when that semantic ranking is enabled and it sees a search query which looks like a question, then it can provide an answer. And this is what you can see here. And you can also see that there are some highlights. In addition to just returning such an answer, it also shows you which part of a given text is related to that query. So for example, when you display such an answer on the UI for a user of your application, then you may highlight some of these parts so that for a user it will be a sign, okay, so that document was returned because of this section of a text. So it's really something which can enhance and improve user experience in your application. So this is about answers. Then we have captions, and captions are somehow also related to answers, but what it does, it returns a document, and then within that document it also specifies which part of that text was the most important while returning such a document. So the concept is similar to an answer, but answer is just something which is returned like at the very top, something like independent. That is the best answer for that question, whereas captions is something which is attached to each of the documents returned. And you can also see that for captions, we have that reranker score. So that score here comes from the L1 phase of the search, whereas reranker score is the L2 phase. And that's the second feature. So we have answer, then we have captions, and the third feature is query rewriting. But I'm going to record a separate video to delve into more details about query re-ranking as a concept, as a technique in general, but this is the third feature. It's still in public preview in March 2026. So this is how it works in a nutshell. And now let's go through the C# example and let's see how various searches are performed. See you there. Let's finally analyze the C# example. Let me briefly describe the security part of that application. If you look here, I'm using default Azure credential instead of API keys, and I encourage you to always use default Azure credential and in general rely on Entra authentication rather than on API keys. What this class does, it behind the scenes invokes various credential classes like environment credential, managed identity credential, Visual Studio credential. And in that application, when I run it locally behind the scenes, it invokes Visual Studio credential. It can obtain a security token, thanks to which I authenticated with my account here in Visual Studio. And I also assigned to my security principal search index data contributor role, because in that example, I push data to Azure AI Search and then I perform a search operation. If I was performing just a search operation, then following the least privilege principle, I would use search index data reader RBAC role. And here I use Azure Open AI Client to interact with both embedding model deployed in Microsoft Foundry as well as LLM also deployed in Microsoft Foundry. And the role, the RBAC role I assigned to my security principal is Azure AI user. So that's the security part in a nutshell. If we go to run async method, you will see that I first read the data from that JSON file and then just push that into that index in Azure AI Search. If we go here, you will see that I literally read data from the JSON file, but in addition, I vectorize one of these fields, which is overview field. Once I have that overview vector, I push all the documents using that search client. So that's the indexing phase. I've invoked it already. And then we have 4 methods to be selected. I would like to focus today on the semantic search. There is a deep dive into about hybrid search in a separate video on the RAG playlist, so you can watch it. But for the semantic search, you will see that what I do here, I create semantic search options. And there are three properties I'm using: query answer and query caption. And this is related to what you can see. Let me paste that query again. This is captions and answers, right? And semantic query. I promised you to explain that mystery. Can we invoke full Lucene query in conjunction with semantic query? And how if that query type has only one value assigned? It's either full or semantic. So how to do it? And you can do it by leveraging that semantic query field. So what it allows you to do, it allows you to perform a different query for the L1 retrieval phase, for example, that full, which uses Lucene syntax, in conjunction with a dedicated question for the L2 phase, for the semantic ranking. Let me show you how it looks like. I don't need to invoke it to use that semantic query in that particular C# example, but it's just something useful to know, so I just wanted to show you that. And if I go here, you will see that now I specified query type as full. And thanks to that, I can leverage, for example, that fuzzy search syntax. So what I specify here is called like that Levenstein distance. So if user made a typo, then if that string differs at maximum 2 positions, then it will still consider it as a match. But then I have to specify that semantic query here. So you can see query type is not set to semantic, but because I'm using semantic query, Azure AI Search knows that it should take that value from the search property during the L1 retrieval and that value assigned to semantic query during the L2 retrieval phase. And yeah, let's invoke it. If I'm showing you that example, let me quickly show you that there is also an option to set a custom tag that will be used to highlight these relevant parts of your results. As you can see here, I specified strong, and in the results, you can see strong as well. So one more time, you can send a different query for the L1 and for the L2 phase of your retrieval using semantic query property. And this is what you can see here. There is one more property, semantic configuration name, but I'm not forced to use it because, as I showed you before, I specified that particular semantic configuration as a default configuration in my index JSON definition, and therefore I don't have to specify it here again. And yeah, let's invoke it now, and I'll show you how it works. Let me start with BM25. Fast and prestige. I chosen such a question deliberately because for BM25 it will be very challenging to find accurate results, because BM25 is great at finding exact matches, but there is no such word like prestige. So you'll see it will have difficulties to find these luxury starships. It returned security, cargo hauler, and reconnaissance. But now if I invoke vector search, it should find more accurate results, right? Because vector search is all about that semantic similarity. Let's try fast and prestige. And it looks better because we have our luxury starship at the second position, but it's still not ideal. And of course, you can also see that reranker score and reranker boosted score, which I will discuss in a second, are both 0 because we haven't performed that semantic search yet. You can also see that score has changed, and that score is an outcome of that reciprocal rank fusion invocation. Do you remember that from these first diagrams? So it just combined the results from the BM25 and vector. Let's carry on. Hybrid plus semantic, fast and prestige. First of all, you can see that there is an answer returned, right, at the top. And then we have top 3 documents which were re-ranked during the semantic re-ranking phase. You can see that the reranker score is not 0 now, it contains a valid value. You can also see that it swapped the places of these 2 starships comparing to the previous example. And it's also visible if you look at the score. The score of the second result is higher than the score of the first result, but it's not the score which is taken into account because we performed a semantic re-ranking, and therefore it's reranker score which is more relevant when ordering these results. And of course, for each of these documents, you can see a single caption which was returned, and each caption highlights the most relevant part of each of the texts. So that's how it works. So I already proved that it improved the accuracy of results, but let me show you one more example. Let me first invoke it, and then I'll explain why I decided to add such an example. It's hybrid plus semantic plus scoring profile, fast and prestige. As you can see, now reranker boosted score is no longer 0, and it ordered these documents also based on this reranker boosted score. First of all, why it ordered it by reranker boosted score? It ordered it because in our definition, you can see that we have boosted reranker score as a ranking order, and that is a default value. But how that query was invoked? So if we go to the C# example here, you will see that if selected search method contains scoring profile, then scoring profile equals, I specified a scoring profile and then I passed scoring parameters. I don't want to delve into too much details, but if I go to that index one more time and to scoring profiles, you'll see that I specified such a scoring profile. And as you can see, I use a single function. That function has type tag. There are also other types of functions. And scoring profiles are used to boost some documents based on various criteria. Not delving into too much detail, just one thing you should be aware of. If you performed a semantic search and you only had such a setup here, category and weight 3, 0, then it wouldn't return that reranker boosted score, because currently when I'm recording that in 2026, in March 2026, you are forced to use either of the functions available in order to order these results by reranker boosted score. So that is that nuance. So that's it. I encourage you to analyze that example. It was a very tiny data set, so it's very hard to show some noticeable differences with such a tiny data set, but I hope that now you know everything and you are ready to implement and add that feature into your project, your application, your architecture. I encourage you to review that code and read the blog post if you are interested. It's publicly available. You can find all the links in the description. Thanks a lot for watching. Thanks for watching. The goal of this video was to show how to leverage semantic ranking in Azure AI Search and why it's such an awesome feature. I also think that it should be considered as a default option for most of the RAG solutions, but now you are equipped with enough dose of knowledge, both practical and theoretical, to maybe implement it in your project. And if you want more content on such topics, future-ready AI solutions deployed in Azure using C# and .NET, then check the other videos on this channel, including the videos on the RAG playlist, and visit the website. Links are in the description below. And if you think that content is valuable to you, then please let me know by hitting the like button. I would really appreciate it. Thanks again for your time and for watching, and see you in the next one. Thanks!